Well, in this lecture, we would learn about the definition of a linear transformation. The definition is just small, very small. It can be learned by heart very quickly if one has to, but it is more important to motivate it. So, most of this lecture will go into the motivation of the notion of a linear transformation. Firstly, we have seen what a vector space is. We have seen what a vector space is. Just to recall, it's a set along with two functions. One is a function which returns to every pair of vectors. We call the elements of V as vectors. To every pair of vectors, it's addition. So it's the vector addition. And the other one is the scalar multiplication, which takes a real number and a vector and returns its scalar multiple. The vector addition is associative, commutative, has an identity, which is called the zero vector, and has an inverse, the negative vector. Okay. So the inverse is, the property of the inverse is V plus minus V is 0. So this is about vector addition. The scalar multiplication has some distributive laws. And what are they? The addition of scalars distributes. The scalar multiplication distributes over the addition of vectors. The scalar multiplication distributes, and the identity or the unit law or whatever. So these are roughly the 9 axioms. So 4 for vector addition, 4 for the distributivity laws of the scalar multiplication, and 1 being the unit law. Okay. So this is some kind of a structure. Now, this is a structure. This is an example of a structure. Now, what is a structure? I will not go into the details or the formal explanation of a structure. In fact, the formal explanation takes us quite deep into mathematics, and it is one of the major inspirations for a very broad branch of mathematics called category theory. But let us try and understand what a structure is very, very loosely. Suppose you have a set of furniture, say some tables, some chairs, just thrown inside a room. Do you come inside and say that that is a lounge? No. The moment these tables and chairs are set up or are arranged in a particular order, in a particular form, that when you come inside the room and say it is a lounge. The same for a bedroom, the same for a dining room, the same for a classroom. It comes with our training from our childhood that we understand that, well, this is a bedroom, this is a dining room, this is a classroom, and so on. So much so, sorry, excuse me, so much so that when we are even asked to design one such, without getting into the formalities, we know what to do, what kind of things should be there, and what is it like, and what should it be. So the notion of a structure is quite natural. It grows quite naturally with us, with our schooling, with our training, and so on. Same with mathematics. A set doesn't have any structure. It is just a loose collection, like a bag. It's a loose collection of objects. It just has the objects. There is nothing to say that one object is better than the other. We can only say whether something is an element of that set or something is not. That much we can say, but nothing more and nothing less. So what is the structure here? Well, over here we do not have only the set, which is V, which is the set of vectors. We do not only have that. We have this vector addition and scalar multiplication. So to each pair of vectors we have a unique vector called its addition and written as V plus W. Well, it's written as V plus W, but we call it the vector addition. So that is a structure that is being imposed on the elements of the set V. Furthermore, to every real number and a vector V, there is another vector called lambda times V, or it's a scalar multiple. So that is also another kind of a structure. So we have two extra components in the definition of a vector space other than just the set of vectors, which is V. So other than the set V of vectors, we have two extra components. One is vector addition and the other is vector scalar multiplication of vectors. So here the structure comprises of the vector addition and scalar multiplication. Now let us come to functions. Well, when we just had sets, what was a function? A function from a set X to a set Y is a kind of a transformation. It takes in each element of X and returns as an output an element f X of Y. So it is some kind of a transformation. Input elements of X, output elements of Y. Okay? But we would now be interested in structure preserving functions. And then what are they? Let us first make this note that functions can be constructed very easily. Structure preserving maps, one has to be little more careful. That means one has to take into consideration a little more conditions. It is not only a function, it satisfies a few more conditions. Now, let us go back to our example which we learned from our childhood days about the structures of a bedroom, of a lounge, of a dining room, and so on. So suppose we have a house and this has a lounge, a bedroom, a dining room, a kitchen, and so on. And obviously these are rooms with several furnitures of several kinds. But they are furnitures and they have some entities inside the room, which makes it characteristic of that kind of a room. Good. Now suppose we want to shift our home. We have sold our old home and bought a new one, and we want to shift. Well, an easy kind of a shifting would be to take hold of some labor, take the entries, that means all the furnitures that we have, all the things that we have, pack it up and just dump it somewhere else. Well, obviously, this person takes just the price, just his labor price. And we then do whatever and we set up our new room. But this person will just take the price of just packing these and just transporting these. But if we are a little more careful and we have the budget to do so, then we would employ a packer and a mover. So this person now comes, looks into the contents that we have in each room, packs them up and takes them to the new home, unpacks them and arranges them exactly as they were to be. So the lounge materials go to the lounge, the bedroom materials go to the bedroom, the dining room materials go to the dining room, and the kitchen. So we can, as if, think this packer and mover is preserving the structure of each room from the old home to the new home. So here it is something similar. So suppose we have two vector spaces, V and W are vector spaces. And f is a function from V to W. So it takes in vectors from V and returns us a V which is a vector in W. Now, what do we mean by the structure preservation by this function? Well, V has the structure of addition. What do we mean by preservation of this addition? So, suppose I take a pair V and a W from V cross V. In V, I could add them. So this is still in V. And then I could transform them to F of V plus W. On the other hand, I can first transform each pair FV and FW. So this becomes in W cross W. Okay. Right. And then I could add, as if in W, to FV plus FW is also in W. Well, obviously, a very natural thing to expect is that F preserves the addition if these two were the same. So that means whether I take a pair of vectors, add first in V and then transform by F, or first transform each of the vectors by F to the vectors V, F, W in W plus W, and then add in W. It doesn't make any difference. So this equation therefore says that we have F preserving the vector addition. Similarly, for the scalar multiple, I can take a lambda and a V, apply the scalar multiplication in V, and then transform it by F, or I take the same lambda. Remember, I have been only given with, I can only transform the vectors of V. So lambda doesn't change. So this is the identity cross F. So this is in, and I apply the scalar multiplication in W, and when I demand this equality, I say that F preserves the scalar multiplication. So when I say that the function F from the vector space V to a vector space W preserves the structure, it means that it preserves the structure of addition. That means we have this equation, as well as when it preserves the scalar multiplication That is, we have this equation. So it is just not a function just not an arbitrary function from v to w, but a function alongside with two conditions: preservation of addition and preservation of the scalar multiplication. So this gives rise to definition of linear transformation, which is precisely functions between vector spaces which preserve the vector space structure. So a function from the vector space V to the vector space W is a linear transformation if for every V W, let's say U and V, okay, V W V, let's make this U, V and lambda in R, F of U plus V is Fu plus Fv. That's the preservation of this is the preservation of addition, and this is the preservation of scalar multiplication. Okay, so it's just as simple as this, but we now understand this in the context of the extra structure that a vector space has, that these are very, very carefully chosen functions which preserve the vector space structure. Let us now look into some examples of this. First, remember the set of reals with its usual addition and multiplication, we have already seen it to be a vector space. And choose and fix. So lambda is a fixed real number. And we take this function. So this is a linear transformation. For instance, let's have another one. Let's take remember R3, well, any Rn with its usual addition and scalar multiplication is again vector space. So what is, these are triples, and I take x plus y, x minus y, 2x plus 3y, and 4 times z. Well, this is also a linear transformation. check. Okay. Let's have a third one. Let's take R4 to P3. Sorry, as far as I remember, I used this. So what is this? This is the set of the vector space of polynomials of degree less than or equal to 3. And what is fx? Well, this is the following. Let's not write it in this way because our indeterminate in polynomials is usually x. So let's say this a plus bx plus cx squared plus dx squared. Okay, let's have another one. Let's see the vector space of differentiable functions you know, the addition is pointwise addition of functions and scalar multiplication is again pointwise. So you know this vector space well. So I am giving you let me take another one, and CR, the vector space of continuous functions. And here is so what do? I take an f, its differentiable functions, I take it to f prime. F prime is the derivative of it. Okay. So here is another one. let Rx be the vector space of polynomials. Polynomial functions. Polynomial functions with real coefficients. Functions f with real coefficients. So here is again so what is it? Suppose Px, I define two linear transformations. So suppose Px is A0 plus A1x plus A2x squared Anxn. N is non-zero. So D of P, if this is Q, this I will write as P prime, and I of P I'll write as Q. What's the formula for P prime x? Well, P prime is A1 plus 2A2x n an x to the power n minus 1, and Qx is A0x plus half A1x squared plus 1/3 A2x cubed plus 1 by n by n plus 1 an. Okay, show that both are linear transformations, and there are several others, as we shall see when we go through this course.